And in order to do that, we're going to change those logarithms into exponential form. So let's do that, So first, recall that from the top part, the log base 2 of 50 is actually 5.644. We found that with guess and check and then comparing. And the log base 5 of 50 is actually 2.431. So it's clear that these two values are not the same, right? Because 5.6 and 2.4 are completely different numbers. But the question asks why. Like, why is that the case? And the exponential form will help us explain that. So the log base 2 of 50, that means I have to take 2, raise it to some number. I'm just going to call it x because I don't know what it is. And I'm going to get 50. And then the log base 5 of 50 means I have to take 5 and raise it to some number and get 50. Because the answer or the logarithm of both of these things is going to be this exponent. So it's got to be the same. Is there any number x that will make both of those true by plugging in the exact same number for both? No, there isn't. There's no power of 2 that coincides with the power of 5. So this is not true because no such x exists, right? So no such x exists. There's no number that I can plug in here that in both cases will give me 50. But it took looking at the exponential form, and you'll find a lot of times dealing with logarithms, especially when they're numeric like this, the exponential form is going to reveal a whole lot more to you and make a whole lot more sense. Because looking at the log, it's just kind of like, what is that? What does that even mean? And I still look at it that way a lot of the time. It's just beyond me. What is that? Is it like a harmless bug? I think so.
I think it's going to kill us all when you leave.
It does not seem aggressive. It just seems stupid. Okay. Which is better. All right. Is anybody allergic to anything like this? Okay, it's fine. It's like some stupid moth. This is on the recording. That's great. It'll live on forever. Wonderful. Super. All right, so for number 11, and I will go ahead and tell you that number 11 is a favorite of mine for a test question. Okay. I love it. Huh? You did? Nice. Okay, so let me explain it to you. And again, this is a place where the exponential form comes in handy. So, what this is really asking is what number can I raise 5, 2, and 10 to and all get the same number? What is the x that will give me the same number in all 3 cases? And there's only one option. The exponent has to be 0 because the only way we're going to get the same number out every time is if we raise 5 to the 0th power, we'll get 1. 2 to the 0th power, we get 1. 10 to the 0th power, we get 1. And so that's the only case where we get the same output by using the same exponent every time. Okay? Does that make sense?
So it's like a tricky but easy one.
It is right. It's a tricky but easy question. Okay, so, and a lot of it has to do with when you look at this, it just looks like gibberish. You don't know what it's asking really, maybe, so you don't know how to answer. But essentially what it's asking, if you write it in the exponential form, is a lot easier to see. What number can I raise 5, 2, and 10 to that'll give me the same number? And there's only one option. Okay. Also, anytime you get some crazy question like this, what are the numbers that behave strangely in mathematics? Well, 0 and 1. So that's always my go-to. Let me look and see if 0 and 1 are involved because they're the weirdos. They're always causing problems. So, all right, let's do this brief little assessment at the bottom. Let me walk through my thinking with you just to kind of highlight how I approach these problems. Based on your knowledge of what the logarithm is, and when I say that or I talk about the definition of the logarithm, what I mean is changing it between the exponential and the logarithmic. That's our main tool for problems like this. So If I take log base 8 of 64, what that actually means is 8 to what power gives me 64? And it would be 2. 8 squared is 64. So my answer in this case is x equals 2. Okay, when I look at the logarithm, I'm going to think in my mind that that is asking me 4 to what power will give me 64. Now, if you're not familiar with higher powers of numbers like that, you can always break out a calculator and just start guessing. In this case, 4 to the third power is 64. But you could figure that out with just a little guessing and checking. I'm not going to give you those weird decimal ones if I ask you to figure something like that out. And if it's on an assessment where you don't have access to a calculator, it'll be pretty common powers, right? I won't ask you like something wild. Okay, it'll be more like this one or this one. So again, log base 2 of 64. Well, 2 to what power gives me 64? You might have to work with that one. What is it? 6. 2 to the 6th power is 64. This one, log base 64 of 64, is really asking me 64 to what power will give me 64? The first power. So x is equal to 1. Okay. This is a throwback to those half sheets. So if 5 to this power is 105, rewriting that into logarithmic form, I'll have log base 5 of 105 is equal to the exponent. And so that's my answer. Okay. It's just moving back and forth between the formats. Let's write log base 2 of 17 in a different way. Okay, sorry, when I hear that, I can't concentrate. So 2 to the 4.088 power is equal to 17. And so then, boom, just rewriting it with the definition of the logarithm reveals the answer. This last couple, I guarantee you, I will put one of these on there. Okay. So these are a little tricky, and they kind of were on the second half sheet, but we'll go over them now. So rewriting this as an exponential would be 5 to some power is equal to 5 over 4. So what must x be? 4, right? So essentially what is happening here is if you have the base of the logarithm is the same as the base of the exponential, they just kind of cancel out. 4. See how the same thing is happening here. The base of the exponential is the same as the base of the logarithm, so they just kind of cancel each other out. Okay? That is always true. Always. So like tomorrow, if I'm like, well, let's do a couple more. Let's say I've got, what is the log base 2 of 2 to the 4th power? That's just 4. What if I say 3 to the log base 3 of 7? Well, that's just 7. Okay. What will not work? Let's do a non-example, right? Let's learn a little more about seeing what isn't going to work out. Let's say I have 3 to the log base 2 of 4. That is not equal to 4 because these two numbers are not the same. And then the other, let's say I have log base 3 of 2 to the 4th. These two numbers are not the same, so this is not equal to 4. So that shortcut only works if the bases of both are equivalent. Okay. Questions so far? I feel like that should address any questions you might have had on this, except for maybe these last two, and I'll do those two on the half sheet for you. And hopefully the key will be sufficient. If not, please feel free to ask me a question. So for this one, it says if log base 6 of 9 is equivalent to 1.226, then this, what is x and y? Just rewrite it as an exponential. 6 to the 1.226 equals 9. And then you just want to use this structure, right? There's the exponent, x is the exponent, so x is equal to 1.226. And of course, by the same logic, y is 9. Is that better? Does that help kind of clear up any issues we might have had on the half sheets?
Can you do number 10 too?
Sure. Let's rewrite that as an exponential. Okay. So I'm going to take this logarithmic expression or equation, I'm going to rewrite it. So 11 is the base, 2.482 is the exponent, and the answer is 384. So again, just looking at how these mirror each other, x is 2.482, and so y is here, and so that's this. So really what you're trying to do is this is forcing you to practice moving between the two forms instead of relying on those quick shortcuts. You're like, oh, that's the only number not shown, I'm going to put that one. That is not what we want. That's not enough depth of understanding to be successful. This is not going to happen. Okay? So real quick, what is number 5?
6.
6. What's number 6?
8.
8. What's number 7?
9.
And this last one? There you go. Remember, you'll see one of these tomorrow. My suggestion to you is if you've already done both half sheets and maybe you want a little extra practice, you can always go look at the blank copy in Classroom and see what you can reproduce without seeing the answers. Best way to get good at math is to do more of it, unfortunately. Or fortunately, however you look at it. All right, I'm going to go through this whole logarithm worksheet. The primary difficulty with this sheet is probably just that we pulled in some of the questions, some of the exponent rules that we learned last Thursday, and I asked you to use both pieces of information.
There's one left on the table.
Ethan, I'll give you one in just a second. Yeah, just you can either write on paper or go back and pick it up and I'll print you one. It's no big deal. Okay, so this wants me to express the equation in exponential form. And if you remember, log base b of x equals y, and b to the y equals x. This is called, this is the definition of the logarithm in general. That's just moving back and forth between exponential and log. All right, so let's express each of these in an exponential form. That would be 5 squared equals 25. Base, exponent, answer. This one would move in the same pattern. Base, exponent, answer. 8 to the 1/3 power equals 2. Now let's take kind of a sidebar and see why that is true. Let's see why that is true. I'm going to do that up here. So remember that 1/3 powers are roots. And so really this is the cubed root of 8. So no going back and forth through here. If it was the 1/4, it would be the 4th root of 8, so on and so forth, okay? That's a throwback to a previous course. All right, let's go to logarithmic form now. So that would be the log base 5 of 125 equals 3. Remember, in the logarithm, the answer is the exponent. All right, let's do this one. This would be the log. What's the base in number 4? 8. Very good. This is the base of the exponential. And so it becomes the base of the logarithm. What is the answer in this equation? Yeah, in the exponential, it'd be 1/8, so that equals -1. Now, why is that true? Let's look. Let's look using our exponent rules. So, what's that?
No,
Yeah,
it wasn't a question.
okay. You were just telling me. Okay. So 8 to the negative 1, what happens if you have a negative exponent and you want to make it positive? What do we do with that? Yeah, you move it. Either if it's on top, you move it to the bottom, and if it's on the bottom, you move it to the top. So if I move this into the denominator, it becomes 1 over 8. So that's why this is true. All right, so if I ask you to evaluate the expression, you can use that. You can use the exponential form to do that. So that means this can be rewritten as 6 to some unknown power equals 36. So what power of 6 is 36? The second, 6 squared. Same thing here. 9 to some unknown power is 81. That's 9 squared, so x is 2. Here's that trick, the trickery, the shortcut. What's the answer for C? 10. It's got that. This base and this base are the same. Let's go find all the other ones. What about 7? 37. What about 7b? 8. 7c? 25. Number 8, A, B, and C are the same. If there's no base listed on your logarithm, what is the base? 10. So these are all base 10. Log base 10, log base 10. And then we see the same instance of the bases being the same. So this is just 27. This is just 5. And this is just 87. If you know what you're looking for, problems like that are very simple, okay? Just remember the bases have to be the same. All right. 6 is a little more difficult. So 6a, let's use the exponential form first. I'm going to use a different color so it doesn't run together. So this would be 3 to some unknown power equals 1 over 27. So the first question I'm going to ask myself here is what power of 3 is just plain old 27? Right, 3 to the third power will give me 27. So if I want that 27 to go down to the denominator, and I can just make that 3 negative. Because let's watch this. 3 to the 3 is 27. And so 3 to the negative 3 would be 1 over 27. So if you see one like this, just understand that you're going to have a negative in the exponent, and you just need to find what power you're looking for. All right. B requires you to understand that the root is really just a power. So this is a square root. So it's really the second root. That's that understood number that we don't see. This is the second root of 10. We just call it shorthand the square root. So we can actually rewrite this. I'm going to come all the way over here to do this one, okay, because I want some room. So this would be log base 10 of the second root of 10. So log base 10, this would actually be 10 to the 1/2. See that pattern happening? The bases are the same. So what's the answer for this one? 1/2. So this is just 1/2. C is tricky because it asks you to, let's first write this in exponential form. So this would be, so this would be 5 to some power equals 0.2. What's 0.2 as a fraction?
1/5.
Yeah, 1/5. So this would be actually 5x is equal to 1 over 5. So the exponent would just need to be a -1. Because 5 to the first is 5. Apply that negative in the exponent and it's going to drop down bottom. All right. Let's do these last ones. These last ones are specifically use the definition, which is rewriting as an exponential to find the x. So this would be 5 to the 4th power equals x. whatever 5 to the 4th power is, it's 625, so that's my answer. Okay, let's rewrite this one. This would be 10 to some power is equal to 0.1. 0.1 as a fraction is what? A 1/10. So 1 over 10. So x needs to be what? -1. Because 10 to the 10 is, or 10 to the 1 is 10. Adding the negative will drop it down into the denominator and give me 1 over 10. All right, let's rewrite 10a, 4 to the x power equals 2. So remember that we could have fractional powers to do roots. If I were to take the square root of 4, that would give me 2, right? And remember that the square root of 4 is really 4 to the half. So x in this case would be 1/2. Then for b, this would be 4 to the 2nd power equals x. So x would be just plain old 16 in this case. For 11a, x to the 3rd power equals 1,000. What to the 3rd power will give me 1,000? 10. Perfect. Right then, last one, x squared, or to the 2nd power equals 25. So what's x? 5. All right. Well done. But it all hinges on being able to rewrite in that exponential form, okay? It makes it a lot easier. Okay, so let's start on the second thing we're gonna work on. I'm gonna give you the exploration. We're gonna look at some properties of logarithms. I'm gonna work through the first section with you, and then I'm gonna give you some time to kind of work through the rest. Then I'll have a second, like a final quick set of examples. We'll have a very short homework practice assignment. It's like 5 problems. We're not going to get through all the notes today. So you'll really just be finishing up the exploration tonight. 5 practices from the notes and getting ready for your homework check. And we'll start there. Ethan, I owe you a sheet, right?
I wrote it down on the paper.
You're good? All right. So like I said, I'm going to walk through the whole first section of this with you. Is the paper I'm giving you right now on your homework check tomorrow?
Yeah.
No, because we're just learning it today. Seems mega rude. I'm not gonna do that. All right. Those of you on the Meet, if you want to open that PDF on Classroom or just follow along on OneNote, that's fine. Okay. Let me see here. You'll need a calculator. Take out your calculator. We're going to do that thing we do where we kind of erase all of this so we can start fresh. This is the second time I've taught this morning. Excuse me. All right. All right, so starting in the top. So I want you to pay a close attention to the parts that ask you to not use a calculator. Because like I mentioned earlier in the week and yesterday, if I tell you not to use a calculator on the work, you should be able to reproduce it without a calculator on the test. So for number 1, we're going to fill out this here chart. So the first thing I want you to do is to put log 3 plus log 7 in your calculator. What are the bases of these logs? 10, right? So we're going to use the calculator because we can. So to the nearest 3 decimal places, the first thing we're doing is log of 3 plus log of 7. into the nearest 3 decimal places, I got 1.322. Next thing, put in log of 21. Also 1.322. So, one instance of something is not enough for a pattern. Let's at least do the second line here. To put in log 3 plus log 5. I got 1.176. And then put in log of 15. 1.176. So it's pretty safe to assume at this point that the pattern is going to continue on down the chart. But what I want to draw your attention to here is the relationship between these two numbers, 3 and 7, and this number, multiplication. Okay. Is it also true in 2? We need to at least check a couple of cases.
Yeah.
3 times 5 is 15. So in general, if I have the log of some number plus the log of some other number, I can write that as a single logarithm of the product of those two numbers. So in other words, the log of m plus the log of m is equivalent to the log of m times n. And we call this the product property for logarithms. This can go the other way also. You might want to make a note there that the log of m times n can be converted to the log of m plus the log of n. So it just depends on where you're starting and where you're trying to go. I will say, and I'll go ahead and warn you, that this should be committed to memory. This particular, you don't have to memorize the formula, you just have to remember this relationship, okay? The product property. We're going to have our first no notes quiz, like legitimate quiz on Friday. So homework checks, you can use homework assignments. Tomorrow there'll be no notes on that one, just your homeworks. And then the quiz is no notes. So this is one thing that you'll need to have committed to memory for that. So just a heads up. This is the product property. So let's take a look at number 7. This is an application of that property. And to apply the product property, please note the capital letters that say no calculators. Suppose you know that the log of 3 is this decimal, the log of 2 is this decimal, and the log of 10 is this one. So what we're going to do is we're going to use what we have found about the product property to find these values. So essentially, let me show you what to do, and then it'll start to make sense. So I really need to use these numbers. I need to rewrite this as the product of 2 of those numbers. So how can I do that? 30 can be rewritten as the product of 3 and 10. So we can say the log of 3 times 10, or m times n, is equivalent to the log of 3 plus the log of 10. That is the product property. We learned that if we have the product in the argument, we can separate it into 2 logs that are added together. I mean, well, what's the log of 3? Well, the log of 3 is 0.4771. 0.4771 plus the log of 10, which is 1. And so the answer there, you would just add that without a calculator back to elementary school. And that's just 1.4471 is your answer. We're going to do the other 2 as well. Okay. Let me use a different color so it doesn't run together. So the next one, we're using the product property. So I want to write 60 as a product. Remember, the product is 2 numbers multiplied together, and these are my choices. So why am I restricted to those numbers in this case? Why? Because those are the ones you have values for. That's the only reason. Those are the values I gave you, so you have to use those because you don't have a calculator. So what combination of multiplication of these numbers will give me 60? Well, I can rewrite this. Yeah, 3 times 2 times 10. So that can be rewritten as the log of 3 plus the log of 2 plus the log of 10. Well, the log of 3 is 0.4771. The log of 2 is 0.3010. And the log of 10 is 1. So the calculation you would actually need to perform, and I'm not going to do it with you. I know you know how to add those, just in the sake of time. Okay? You would perform that calculation, and that would be the answer here. And then finally, let's do the log of 20. We'll do that in green. So I need to write 20 as a product of these two numbers. Well, that would just be 2 times 10. So that would be the log of 2 plus the log of 10. And so you would just grab those decimals that are those values and add them together, and that would be your answer for the log of 20. So what this does, and the reason I do it without a calculator, is it forces you to utilize the product property. Okay? Because there's no way you know what the log of 30 is, the base 10 log of 30, without a calculator, unless I give you that and you're able to use those values. So what I want you to do next, I'm going to give you probably 15 to 20 minutes to make it as far as you can through this before I show you some more stuff. And I'll kind of hit some high points. Is you are going to be looking for the same thing in part B. Notice you have a table. It asks you to find some relationship and figure out the property. And it asks you to do the same thing. There are two challenges. Let's kind of bring it together and finish talking about these properties. I'm not going to go through the whole exploration of parts of that I want you to do and get some practice with, and we'll finish going over that tomorrow. But I do want to make sure that you know the properties before we move on, okay? All right, so let's talk about quotient property. Quotient property, hopefully we discovered that the log of some number m minus the log of some number n can be rewritten as a single logarithm as a quotient. So that's m divided by n. Okay? Because 15 divided by 3 will give me 5, 35 divided by 5 will give me 7. And then conversely, right, we can go in the other direction. So if I'm given a quotient, I can write it as 2 separate logs, one subtracted from the other. Back up there. There we go. Log n. Okay. So that is the quotient property. This is another one you need to be able to apply from memory. Okay, let's do product property or power property. Sorry, power property. So the power property just takes the power and swings it up into the argument here. So this would actually be n to the m power. And so effectively what happens is this power of n just swings down in front of the logarithm. Okay, it just goes whoop, just like that. So basically, again, if you had log of some number to a power, you would rewrite that as m times log of that number. It just goes just like that. So when you're working through these, you'll just need to write this number as a power, right? We can write 9 as 3 squared. We can write 100 as 10 squared. We can write 8 as 2 to the third, and so on and so forth. Now, down in this last part, all I am asking you to do in part D, and these are definitely test questions. I know these are on your test, and I think there's one on your quiz as well. So just FYI. I would need to write 100 as a product, a quotient, and a power. You are not restricted to any special numbers in part D. Use whatever numbers you want. So 100 as a product, I could write 50 times 2. I could write 4 times 25, whatever. As a quotient, I could write 400 divided by 4. I could write 300 divided by 3, 200 divided by 2, whatever. As long as it's some quotient that gives you 100. And the power property, I could write 100 as 10 to the second power. And so then I would just take those things and I would express them as a sum, right? So that'd be the log of 50 plus the log of 2, the log of 400 minus the log of 4, and then the power property, I would write 2 times log 10. These are the answers for part D. So you're just going to do that for the remaining numbers that I give you. This is what you're just going to stop here. I don't expect to have any specific value or you to give me a number. I just want you to rewrite it in that format. Okay? All right. We'll go over the answers for that tomorrow. But now you need a piece of notebook paper. While I do that, let me, the title of your notes is there in red.
I don't understand how to.
I try to move through these few examples really quickly, so if you have questions again, you can always just ask. All right. I just think it's 10,000 times easier with the letters.
Is this what we're about to do later?
I just think it just makes good sense. So, all right, so we are expanding and condensing logarithms. And when we expand, we write it as a bunch of separate logarithms. We're not going to get to condensing today. We're just going to do the expansions. And so in order to do this, I'm going to use the three properties that we just learned. Okay, we're going to use product, quotient, and power properties to rewrite these. So notice right now, it's a single logarithm. I'm going to stretch this thing out to where it's a bunch of logarithms. Okay? So the first thing I want to do here is I want to recognize that inside the argument of the logarithm, which is just what's inside the log, I've got a product, which is multiplied together, and I've got a power. So the first thing I'm going to do is I'm going to apply the product rule. I'm just going to write a note out here. So that's what I'm doing.
And a U or a Y?
That's a U. My Y is lit like that. Okay. So this would be the log base 9 of U plus the log base 9 of V plus the log base 9 of W to the 6th power. So I've just taken everything multiplied together and wrote it separately as being added.
So that's U, right?
It is a U.
Is there any reason why it's like that? Like that variable?
Nope, these are arbitrary. It could be A, B, C, truck, banana, car, whatever. Doesn't matter. It's just some arbitrary placeholder for unknown numbers that are different from each other. Okay. So we're almost done. I can't leave this here for a full expansion. So now I'm going to apply the power rule to get rid of it. So this one doesn't have any powers, so I'm just going to leave it. That's as expanded as that gets. This one doesn't have any powers, so I'm going to leave that one also. This guy has that power of 6. And remember, the power rule tells us to bring the power down and multiply it in front. So this becomes 6 times the log base 9 of W.
Do we have to show like the middle step?
Nope, you may skip steps in this. Yep. I just show it step by step so that I'm not doing too much at once for you to catch on to what's happening. I do not mind you skipping steps here. So this is your fully expanded. And you know it's expanded because there's only one thing in the argument. Remember, the argument is what's inside the log. So it's just the log 9 of something. Log 9 of one thing. 6 times the log of one thing. That's a fully expanded logarithm. No exponents, no products, no quotients inside. Okay, let's do the next one. So when you look at something like number 2, before you even start applying the rules of logarithms, you need to make this look like a product, a quotient, or a power. It currently does not look like a power. There's a root. But I don't recall learning about the root rules for logarithms, right? So let's change this real quick. Remember, this is a square root, so that it's a root. It's the second root. So I can rewrite this as the log base 9 of u times v times w to the 1/2 power. Remember, square roots are to the 1/2 power, third roots are to the 1/3, and so on and so forth. And I do that because I have a power rule. Again, I don't have a root rule, I have a power rule. All right, so at this point, I'm going to use just plain old rules of exponents going all the way back to last Thursday. Remember, each item inside gets that 1/2 power. So let's do that intermediate step. This will be log base 9 of u to the 1/2 times v to the 1/2 times w to the 1/2. And there's another way to go through this one, and I'm just showing you this one right now, okay? All right, so now I have a product inside. I can apply the product property, so I'm going to do that now. This is the product property. So this will be the log base 9 of u to the 1/2 plus the log base 9 of v to the 1/2 plus the log base 9 of w to the 1/2. Okay. Well, now we're kind of at a similar place where we were in the first one, to where the only thing left are those powers that need to be dealt with. So now we'll apply the power property, and we will bring all these exponents in front of the logarithms as a multiplication. So that's 1/2 times the log base 9 of u plus 1/2 times the log base 9 of v plus 1/2 times the log base 9 of w. And that's it. Now, I will say there are two different ways to look at this answer, right? I need you to know both of them, be able to recognize both of them. I'm going to show you the other one in blue. Okay, these are both the same exact thing. This is the log base 9 of u divided by 2 plus the log base 9 of v divided by 2 plus the log base 9 of w divided by 2. These are the same thing. I will accept either. But like if I gave you a multiple choice type question and the answer looked like this, I would need you to know that these two are the same, right? That makes sense? Why is that the same? Well, multiplication by 1/2 is the same as division by 2. Agree? Half of 4 is 2, and if you divide 4 by 2, you get the same thing. That will be that'll be super useful to you later. I just want to kind of get you used to looking at the different ways you can express the same thing. That's like what 95% of the whole class is about. How can we change how it looks? All right, so answer in highlight either is acceptable. These are the same thing, but you need to be familiar with both. Fair enough? I think I got one more example left. Here it comes. All right. So let's look at it. Let's look at it and figure out first kind of where our plan of attack. Remember, I got quotient, product, power. Do you see a quotient inside the log? Quotient is division. Yep. You see powers? Yeah. So we're going to use quotient and power rule on this one. So I'm going to use the quotient rule first. Let me write that out here. I'm going to use the quotient rule. Use a lot of the vocabulary because, like on your test, I'll say things like use the quotient rule, and I need you to know what that means. Okay. So remember, for the quotient rule, I'm going to take the log of the top, log base 6 of x to the 4th, and then subtract the log of the bottom. So that's log base 6 of y to the 6th. So I just said log this minus log of this. Okay, what's the only thing left inside my logarithm? I ain't got a quotient, I don't have a product, I've just got a power. Excellent. So if I just bring those powers down front, I'm gonna be done. I'm gonna use my power rule for that. So this would be 4 times the log of 6x minus 6 times the log base 6 of y. That looks like a b. That's lame. Let me fix that. All done. How do you know when you're finished?
When it looks, no.
When it looks right.
Yeah.
Okay, here is an analytic way to be absolutely certain that you are finished. When the logarithm is fully expanded, you just gonna have one thing in here. Not two, not something to a power. You're just gonna have one thing, and it's just y. It's not y to a power, it's not x divided by y, it's not x times y. I know I'm done when there's just one thing in each logarithm. Okay, that's how I'm finished. That'll do. I'm gonna like I said, there's only 5 practice problems on this whole sheet because we're not done yet. We'll finish it up tomorrow. But that's all the notes I have. You have like 20 minutes left. None of this is on your homework check tomorrow, but I do want you to be ready to ask questions. But it is numbers. It is numbers 1, 4, 9, 11, 12. And that's here, but it's also under the assignment in classroom if you forget, okay? You can go click on the assignment, read the instructions that are on there, and it'll say 1, 4, 9, 11, 12 if you forget which ones. And then just, play some cleanup on your exploration. I'll go over that tomorrow, take our homework check, finish these. Maybe our test will be on Friday next week. Very nice. Very good.
What time are you gonna have this class?
11:20. So you got a bit. All right, my meat folks, I'm done with like new stuff. And I'm just going to leave it on and I'm going to stop the recording, but I'm going to leave the meet open until the end of class in case you have questions.